So this lecture will cover yield to maturity. And now yield to maturity is the most popular measure of yield in the bond market. And it's the rate that equates the present value of a bond's cash flows to its price. And we can say that the bond's yield to maturity is its internal rate of return. Now, internal rate of return is the expected rate of return inherent or internal to an investment's cash flows. So, for instance, let's just look at a one-period investment where we expect to receive $110 1 year in the future and costs $100. We can easily calculate what's called the internal rate of return. It's the rate of return inherent in those particular cash flows. We invest $100 and get $110 1 year in the future. The internal rate of return would be 10%, and we can find that just by solving the future value formula, where the $110 comes from the 100 compounded at that one rate one time. So if these cash flows belong to a bond, then this 10% here, these cash flows internal rate of return, would be called its yield to maturity. So the yield to maturity is the bond's internal rate of return. It's what is expected or promised if the bond is held to maturity. So the yield to maturity, like the internal rate of return problem we just saw, is found by finding the rate that makes the present value of the bond's cash flows equal to its price. So if we set up a bond valuation formula here where the price of the bond is equal to, and since the yield to maturity is that rate of return that makes the present value of the bond's cash flows equals to its price, this yield to maturity is held constant for the whole term to maturity. So given that, we're looking at a constant discount rate, and given that the bonds are form an annuity, we can say that the price of the bond, or the value of the bond, is equal to the present value of the coupons, which form an annuity. So we can use the present value of an annuity formula here. And then take the present value of the par value there in the future, which is just a future value. We're taking the present value of that future value. And the idea is to solve for R here, the rate. Solve for the rate. And that would be the bond's yield to maturity. It's the constant discount rate used to take the present value of all these cash flows here and make them equal to the price. Now, this requires a trial and error process, since the yield to maturity cannot be algebraically isolated. So in other words, we just can't solve this formula. Let me just go ahead and use rate here instead of yield to maturity. We can't solve this formula and say the rate equals something. We can't isolate that rate like that. So what we're going to have to do is plug in a number into that rate, plug in a rate, solve, and if the present value of these cash flows equal the price, then we've guessed the right rate. Okay, so let's look at an example. Let's look at a bond that has a coupon rate that's equal to 5%. The term is 6 years. The par is $1,000. And the price is $900. So notice the bond is selling at a discount, and the coupon rate here is 5%. So in order to find the coupon, we simply multiply the 5% by the 1,000. That gives us $50. And for simplicity, let's just assume these are annual coupons. So instead of getting $25 every 6 months, we're looking at $50 per year over a term of 6 years. So in the 6th year, we'll receive our last $50 payment and the $1,000 par value. So these cash flows here are priced at $900. So in order to set up our equation to find the yield to maturity, we're going to be setting $900 equal to the present value of these cash flows, the 50 and the 1,000. The $50 is a 6-period annuity, so we're going to set the $50 up as an annuity and find the present value of that annuity. So we have a $50 payment here. That's our coupon. Total of 6 coupons. We have $1,000 6 years from now that we discounted back at that yield to maturity. So our problem is to find that yield to maturity measure. It's the discount rate used to find the bond's price. Now we need to guess. So what are we going to guess? Well, think about this. If the price of the bond were equal to the par value, which in this case is $1,000, what would the yield to maturity measure? What would the yield to maturity be? It would be 5%, which is the coupon rate. If the yield to maturity, if the rate that we're discounting these cash flows is equal to the coupon rate, then our price will be equal to the par value, here $1,000. Now, is the price $1,000? No, the price is not $1,000. The actual price is below $1,000. We're looking at a bond selling at a discount. Now, how in the world can a bond sell below its par value of $1,000? The rates must have gone up. The rate that we're using to discount the cash flows here has increased above 5%, or they're set above 5%, so that we're getting a smaller present value. So, since the price of the bond is not equal to the par, which in this case is $1,000, we know that the yield to maturity here is not 5%. And so, as you said, as rates go up, the present values or prices go down, and as rates go down, the present value or the price, the value, increases. So whatever rate we guess, the yield to maturity is going to have to be what? Greater than 5%. So let's try 8%. Oops, what happened? We're reverted back there. There we go. Let me just put a question mark there. Is the yield to maturity 8%? Well, when we plug the 8% into our bond valuation formula, we come up with a price of $861.31. So is the bond's yield to maturity 8%? No, if the bond's yield to maturity were 8%, then this, when we plug it into the bond valuation formula, it should come up to be $900, but it's not equal to $900. And so since using 8% does not give us a value of $900, we know the yield to maturity is not 8%. So we're looking to find $900. So what should we do? We know then that it's not 5%. It's not 5%. It's not 8%. So what is it? Should we continue increasing the rate, or should we decrease the rate? All right, you're saying we should decrease the rate, and why is that? Okay, in other words, by decreasing the rate, we can make the present value go up. By using 8%, we have $861.31. We don't want $861.31, we want $900. So in order to get to $900, to move from $861 to $900, that's an increase in the present value. So we have to decrease the rate. So what if the yield to maturity were then, let's try 7%. Is it 7%? Well, if we plug 7% into our bond valuation formula, that gives us a price of $904.67. So was our yield to maturity 7%? It's pretty close, but not exact. It's not equal to $900, but that 904.67 is pretty close to the 900. If we wanted to get more, well, one thing we need to realize here is we've kind of narrowed it down to a range, though. It wasn't 5%, it wasn't 8%, but up here we knew it was somewhere in between. It was greater than 5%, okay, and less than 8%. That's our yield to maturity. And so now we've narrowed that range down, okay? If we wanted to try another yield to maturity, if we wanted to try another rate to find the yield to maturity, what rate should we use? Something greater than 7% or something less than 7%? So a little bit greater than 7% because we want this 904 present value to go down to 900. In order to make the 904 present value go down, we have to increase the rate, okay? So that means that the rate, the yield to maturity here, is less than 8%, but greater than 7%. And we see that this present value here is a lot closer to the price we're trying to find using 7% than 8%. So it's probably going to be very close to the 7% mark, so 7.1, 7.2. We can keep on using trial and error and come up with an exact yield to maturity. And if we continue this process, we're going to find that the yield to maturity is equal to 7.105%. So if we were to try 7.1, well, that's still too low. If we were to try 7.2, that's too high. So then we start trying in between 7.1 and 7.2. We're finally going to end up with 7.105. So again, the yield to maturity is the bond's internal rate of return. It's the expected rate or the promised rate of return for a bond if you hold it to maturity. And there's no nice solution, algebraic solution to find yield to maturity. We have to use this trial and error process. Any questions?
So we can't use this constant rate with the ones that we did yesterday with the plus.
Now let's find the yield to maturity using a financial calculator. We're going to use a bond with a coupon rate of 5%, par of $1,000, term to maturity is 6 years, and the price is set at $900. So we can pull out our financial calculator, make sure that we're clear these time value of money keys, second, clear TVM, and we can go on down the row and put in our cash flows here. Here the coupon rate is 5%. We can assume that that 5%, for simplicity for this lecture, is for coupons paid annually. So 5% of 1,000 is $50. So our annual coupon is $50. That's our payment that will occur over the life of this bond for 6 periods, 6 years. The par value is $1,000. That occurs in one single amount at the end of the bond's life 6 years from now. And so our N is 6. Our price will be 900. That's the present value. So 900 And I'm going to make that negative because the price cash flow is going in a different direction than our coupons and par value. So I entered our par value and coupons as positive cash flows. So those would be the cash flows coming to the investor. In order for those cash flows to come to the investor, the $900 must be an outflow to the investor. So that's why it's negative. We enter that as a present value, and then all we have to do is solve for this I to the Y. Now, the finding yield to maturity is a trial and error process, and that's what the calculator does, or any spreadsheet does, is go through the trial and error process. It just does it a lot more quickly than we do. So we say compute I to the Y, and it comes up with the yield to maturity of 7.104746815. So I think 7.1% would be good for our purposes. Now let me skip this right here. Any questions? Okay. So for this segment, no, I'm reverting back to my former page. So for this segment, we'll be finding yield to maturity for a bond paying semi-annual coupons. And we'll use as an illustration a bond that has a coupon rate of 5%, par of $1,000, a term to maturity of 6 years, and a price of $900. So our annual coupon, given this right here, our annual coupon is equal to the 5% times 1,000. That's $50. So what's our semi-annual coupon? $25. $50 every 12 months. But it's really going to be paid out as $25 every 6 months. So 5% per year paid out every 6 months though. So we need to make a few more adjustments. Well, one more adjustment here, and that is this term to maturity. The term to maturity is 6 years, but in our bond valuation formula, we're taking the present value of these coupons here, and these coupons are paid out every 6 months. So what will our N be here for our present value of an annuity formula? 12. We have 6 years, but these coupons are paid twice per year. That's going to give us a total of 12, or 2 times 6, 12 coupon payments. So 12 periods. We'll be discounting 12 of these payments. And then the par value of $1,000 will be 6 years from now, or 12 6-month periods from now. Let me go ahead and put our $25 here. And I've made a mistake really in this formula, and that is I've placed yield to maturity here in for the rate. However, this rate that we're solving for is not the yield to maturity. The yield to maturity is a nominal annual rate. This rate that we're solving for here will be a 6-month rate. So let me just put R therein instead of yield to maturity. And again, we can't algebraically solve for our rate. We have to use trial and error process. But when we do use that trial and error process, just as if we were finding the yield to maturity for a bond that pays annual coupons, we can find that that rate is going to be equal to 4.435%. And that right there is our semi-annual yield. The yield to maturity will be twice that, 4.435 times 2 to get us a nominal annual rate, and that's going to be 8.87%. And so the 8.87% is the yield to maturity. It's called the bond equivalent yield. It's simply a doubling of the semi-annual yield to get the annual yield. Now you may realize this right here is not an effective rate. In other words, if we made 4.435% every 6 months, then our actual rate of change or our actual return for the year will be something greater than the 8.87%. By doubling the 4.435, we are ignoring the compounding in the second 6-month period of the interest we receive or the coupon we receive in the first 6-month period. So the 8.87% is not an effective rate. 4.435. Really? Well, maybe I'm messing up here then. All right, we got $1,000 future value. 12 is our in. 25 is our payment. 900 as our present value. Compute I to the y. Yeah, 3.537. Where did I get that from? I must have just punched something down wrong. I have everything written correctly here. 925, 12, 1,000. Let me change that then. So that really will be, what is it? 3.5371. 5371. And then we multiply that times 2, 7.07%. Okay, let me correct that real quick here. That's 3.5371%. And then that's going to be 7.071%. Okay, the 7.071%. All right, sorry about that. I wonder if I put in maybe 50 for payment. No, that's not it. I wonder what I did wrong.
6 years in?
Try that. 4.43. Yep, that was it. I had 6 years. All right. Any questions though? Again, we have to take this is the actual semi-annual coupon, make 12 6-month periods. So our semi-annual yield is at 3.5371. And then that's the 6-month rate, but the yield to maturity is going to be quoted as an annual rate. So we take that, multiply it by 2 to get the 7.07. Now, what's that?
Smaller than 17.
Oh, using the annual rates, 5%. Yeah.
Like the IRR for the annual one is higher than the IRR for the semi.
Yeah, you're not going to come up with the same, well, because number one, we're looking at $50 every year being discounted a full year every time, okay? And here we're looking at just $25 being discounted 6 months every time. So we have more, we have the cash flow spread out more evenly throughout the bond's life. And so given the same $900, that would make this discount rate here different, make it smaller there. Now, as I said, this isn't an effective yield, okay? Remember before when I was looking at finding the price of a semi-annual coupon bond, and we started off with 10%, and then I cut it in half to 5%, okay? The reason I could do that is because I was assuming that the 10% was quoted like this yield to maturity here, and the 10% was a result of a doubling of the 5%. So if we take the 7.07%, that's the annual yield to maturity. People see that for a semi-annual coupon bond, that's a result of what? The doubling of the 6-month yield, you see? So why can't we just quote yield to maturity as an effective rate? Well, it's really just to make things simple. We quote things on annual, we can cut it in half instead of having to do the backtrack. In other words, if you wanted the actual, really that's where the 4 point something whatever came from. If you take 10% for the year, and that's the actual effective rate for the year, and you wanted to find 2 6-month rates that when compounded would give you the 10%, you would have to go 1.1, we'll take the square root of 1.1 minus 1. And that gives you 4 point something percent. So 4 point something percent for the first 6 months, and then 4 point something percent for the second 6 months. That's going to compound on the initial 4 point something percent. That's going to give you a total of 10%. You see, so the effective rate is 10%. Well, what do we have to do to find the 6-month rate? Well, then we got to take the 1.1, the square root of 1.1 minus 1 to get the 6-month rate. It's just simpler to say, put everything in nominal terms, like an APR, and then cut it in half when we need to, is the idea. And it's not much of a problem as long as everybody understands that. Okay, so one more thing here in my note I got to fix there. There we go. Oh, and it's about time to go. So sorry about that little goof up. I can't keep this for posterity. That'd be one of the things I can cut off there. But I'll try to save as much for you and put the videos on Angel. Did anybody check out the videos I put up on Angel from the Wednesday's lecture? You see, I cut them up into the smaller chunks. And that way I can cut out any distracting conversations, any mistakes, any retries.